This lesson's on standing waves on a string. First, let's review a few concepts. So remember that when a wave or pulse encounters a fixed end, we get inversion, it flips upside down, and when it encounters a free end, it stays upright, like we see here, pointing in the same direction. Also remember that when two waves or pulses are in the same place in the same time, when they overlap, we get superposition, and we add their amplitudes, their displacement algebraically, to get the resultant amplitude, like this. So reflection from a fixed end results in inversion, while reflection from a free end, we get the wave upright or pointing in the same direction it was before, and superposition can result in constructive interference if the amplitudes are pointing in the same direction, and destructive interference if the amplitudes or the displacements are pointing in opposite directions. This animation is from a different site. You can see the URL here, and what we're going to see is this traveling wave in the red moving towards the right where there's a fixed end. The red and the red outline is showing you the incident wave, and once it hits the fixed end, it's going to invert, and we're going to see the blue reflected wave moving back to the left. The black dots show the outline of the resultant formed by adding the red incident wave and the blue reflected wave. Let's take a look and see what happens. So here's the red incident wave moving towards the fixed end. We will see that it flips when it hits the boundary. Now we see the upside down reflected blue wave, and notice that we've got this black envelope here of the resultant wave. If you look at what's happening with that resultant, you can see that there's actually a fixed pattern forming where the black resultant is not moving left or right like the red incident or blue reflected wave is. Rather, it's staying in place and just swinging back and forth. There are places where the amplitude of the black is double that of either the incident or the reflected wave. For example, over here where we see repeated superposition of the maximal amplitude, and we also see places where it's not oscillating from the baseline at all, where the maximal amplitude of each of the incident and the reflected waves are pointing in opposite directions, and so they're always actually summing to zero. We call these spots nodes, and the other spots where we have a maximal displacement from baseline are called antinodes. So again, we've got a moving red and blue pattern, but the black pattern is not moving left or right, it's staying fixed in place and swinging backwards and forwards. This is called a standing wave pattern. So again, a standing wave pattern is formed by continuous waves reflecting. And when continuous waves reflect, the incident and the reflected waves can interfere with each other, or they do interfere with each other. Now, at most frequencies, and we'll look at this in a moment, at most frequencies, the pattern of superposition is going to be constantly changing throughout the string, and we don't see much of interest like we just saw there. But at a few particular frequencies, which implies a few particular wavelengths, if those are just right, then we'll get constructive interference always happening in the same place, and we'll have destructive interference always happening in the same places along the string. And when that happens, the resulting wave pattern actually stays in place. It's stationary, and so we call that a standing wave pattern because the pattern is stationary. Again, only certain wavelengths will create a pattern that fits on the string. And remember that the wavelength and the frequency are related by the universal wave equation. If we set one, we set the other, because the speed of the wave on the string is determined by the medium. And once again, while the component waves that are underlying the pattern travel, the pattern itself that's formed by their superposition is what's not moving along the string. So I often think of it not as a standing wave, but as a standing wave pattern. And just coming back to the animation, once again, remember that we have spots where we have complete constructive interference, like here, and we call those antinodes, and we have sites where we have complete destructive interference, and we call these nodes. The A and the N here stand for antinode and node. So once again, nodes are sites where there's complete destructive interference, and the amplitude at those spots is zero, while antinodes are sites where there's complete constructive interference, and the amplitude here is double the amplitude of the component traveling waves. Now, when we put transverse waves on a string, the fixed ends of the string must be nodes in the pattern. That's a requirement for the pattern to fit on the string. But because multiple different patterns can fulfill that requirement, can fit on the string, there are multiple wavelengths and multiple frequencies for which a standing wave pattern can occur. Again, remember that wave speed is determined by the medium. So in keeping with the universal wave equation, if we wanted to create a new pattern with half the wavelength, we would need to double the frequency to maintain the equality. So for wavelength to have, frequency must double, and that same kind of mathematical relationship continues to other patterns as well. This simulation's from O-Physics. We see a vibrating tuning fork creating waves on a string. The tension in the string is set by this hanging mass. We have a linear density and a tension, which are effectively defining the medium and therefore the wave speed. And we have this vibration frequency that we've set at 125 hertz. And notice here that we get a standing pattern. In this animation, we can't see the underlying traveling component waves. Now notice that if I increase this slightly, I no longer see a standing wave pattern. This frequency doesn't create a pattern that fits on the string. But if I get to 140 hertz, or as close as I can here, we see another standing wave pattern with a different number of loops. Similarly, if I decrease, I also don't see nice standing wave patterns at every frequency, but when I get down to certain frequencies, for example, if I get close to 94 hertz, then I'm going to see another standing wave pattern. And so there are only particular frequencies that result in the right wavelengths for the pattern to fit on the string. Let's take a closer look now at a few of those patterns. So I've got fixed ends here for each of the strings that I'm going to draw, and the first standing wave pattern that we can form that has the smallest number of loops, or the longest wavelength, is something that looks like that, just like a long skipping rope being held by two people. And I'll draw for each of these a dotted line to show the other extreme. So this is half a wavelength. It is a 1/2 wavelength loop, and we call this the first harmonic. We also call it the fundamental frequency. And in this case, the length of the string from here to here is exactly 1/2 of a wavelength. That is the first pattern with the longest wavelength that we can fit on this particular string, because we need both ends, this end and this end, to be a node, and no simpler pattern would do that. If we increase the frequency now, we can get another pattern that looks like this, which is one full wavelength fitting on the string. So we have 2/2 wavelength loops. We call this the second harmonic, and the length of the string, L, is equal to the wavelength of the standing wave pattern, which is actually also equal to the wavelength of the incident and reflected waves as well. We call this the second harmonic, and the frequency to get to this is double that of the first. So let me explain. If I go from here to here, you can see that the wavelength is halving. The wavelength here is twice as long as it is here. So if the wavelength is going to be multiplied by 1/2, then the frequency must be multiplied by 2 to maintain the equality of the universal wave equation. So the frequency that we are oscillating with, if you imagine something vibrating here just to set this going, must be twice that as in the initial case. If we continue and we increase the frequency even further, we can get the next pattern. The next pattern has 3/2 wavelength loops and will look like this. So we have 3/2 wavelength loops. We call this the third harmonic, and here the length is equal to 1.5 wavelengths. And again, this is at 3 times the initial frequency. So when I say that, I'm talking about, for example, if this had been 125 hertz, this would be 250 hertz, and this would be 375 hertz. And again, that's because to get from the fundamental frequency to here, we've multiplied the wavelength by 1/3, so we need to multiply the frequency by 3. And continuing the pattern, if we go up once more, we can fit 2 full wavelengths on the string. We would call this the fourth harmonic. We get it at 4 times the fundamental frequency, and here the length is equal to twice the wavelength. Again, notice that we have nodes in each of these. So the nodes are here, and we're adding one more node each time we go up in the pattern. So all of these points in the pattern are nodes, and we add one more node each time, and it's always, in this case, one greater than the number of the harmonic. And we also have antinodes that are here in between each of the nodes. And I won't go back and label all of them, but you can see that that's the pattern. Just to show you this as an animation, here's another animation from O-Physics. This is a standing wave on a string with 2 fixed ends. Here we see the first harmonic. This is an animation of the second harmonic, 2/2 wavelength loops, and here's the third harmonic. So that's an introduction to standing waves and standing waves on a string.